Sir, good morning, sir. Sir, good
Good
morning.
morning.
Sir, we'll start our
Hi, good
session with the
morning.
next one. Yes, sir. Good morning, sir. We'll start our session with the next 5 minutes, sir. Now only everyone is joining, sir.
Okay, no issues.
Okay, sir.
Am I audible and
Yeah,
my
it's
video
audible,
is
sir.
okay?
Yeah, it's okay, sir. It is visible, sir.
Uh,
Okay, so we'll start
okay.
with the next 5 minutes, sir.
No problem.
Okay, sir. Thank you, sir.
Already I'm trying to open my PPT.
Yeah, yes, sir. Okay, sir. Good morning, all. Sir, Sir Jairat, sir.
Good morning.
Sir, can we start, sir?
Yeah. Should I start or?
Yeah, sir, we can start, sir. Others, let's join during the session itself, sir.
Okay.
Okay, sir.
So,
So now,
good morning to all.
good morning, all. Introduction, sir. So now I request our coordinator to introduce our Dr. S. Jairat, sir.
Okay, that's what I asked.
A very good morning to one and all. So, good morning, sir.
Good morning.
Good morning, sir. Okay, I'm here to introduce about our Dr. S. Jairat, sir, dignity person here. So, Dr. S. Jairat, sir, professor from NIT Calicut, working in Department of Mechanical Engineering, has completed his PhD from IIT Kanpur in the year of 1988, and he has around vast publications in several. He has vast publications in several journal articles, book chapters, conference proceedings, and he has achieved several citations and H-index in several Scopus websites and SCI. And he is also an active member of Indian Society for Technical Education, Energy Conservation Society, and Institution of Engineers. And his expertise in several thermal sciences. Now I hand over the session to Dr. S. Jairat, sir, to carry over the session, sir.
Okay, thank you for the introduction. Very good morning to all of you again. On the outset, I thank Professor Prabhakaran, Vice Principal Academics, who invited me for this, and also I thank all the coordinators of this FDP program for involving me for a lecture here today. I hope you are having good sessions for the last 2 days. And today I'm going to present one of my students' work who recently graduated from NIT Calicut. And I have recently retired from NIT Calicut service and hopefully take up a new assignment in the near future. Is it possible to share my screen?
Share the screen, sir.
Hello?
Yes, sir, you can share the screen, sir. Yeah, sir.
Okay.
You can share the screen, sir.
My screen should come here, right?
Yes, sir.
Yeah, this one. Is it visible?
Yeah, yes, sir. It
there?
is visible, sir. It is visible, sir. It is
Okay.
visible, sir. Okay, sir.
Okay, thank you. I hope
Thank you, sir.
we'll go without interruption.
Yes, sir.
As I said, the title I am going to present today uh, belongs to the work done by one of my students who graduated in the year 2020, who has done some experiments with solar water heater, ETC type solar water heater, and his main aim is to see the possibility of latent heat thermal energy storage incorporating in the domestic solar water heater. And also he has done some computational work related to that. I thought this may be useful for the participants of this FDP. Mostly I understand that you belong to the group of people aiming to start a PhD work, or somewhere in the middle of your work, or maybe recently graduated PhD holders who are aiming to start guiding new students. And you are free to stop me at any point and raise any questions you want, or the email ID and phone number I have given here below my name. and you can contact me uh, in future for any requirement related to this. Okay, so on the background, all of you know that we are in the verge of a mode change from conventional energy source utilization to non-conventional energy source utilization. And mostly this non-conventional energy source should come from solar energy, directly or indirectly. And we are aiming to have installed capacity of 100 gigawatts solar energy harnessing by this year end. And global mission towards green energy technology obviously should start from our homes. And mostly we use hot water systems by means of solar collectors. Nowadays, it becomes conventional water heating systems in ordinary homes. Almost every new house have a water heater, solar water heater installed at a reasonably small price. And 85% of our domestic hot water energy comes from these solar water heaters. And if you replace the electric geysers by a 100-liter uh, solar water heater, maybe ETC type or uh, copper plate type, you can aim for saving something like 3 to 4 units per day in the form of our electricity bill, electricity consumption. What we aim basically in this work is to have some additional savings. And in the beginning itself, I have given my conclusion here in the last line. We are aiming to save about 10% of energy by incorporating some sort of phase change material in the conventional solar water heater uh, by way of saving energy, or in other words, reducing the size of the existing solar water heater. The motivation of this work come from the growing energy demand increasing continuously, and availability and post harvesting issues with respect to conventional energy as well as non-conventional energy. And if you think about solar collectors, we have tracking issues and design issues of the basic systems, and something like, for example, thermal conductivity related issues, etc. And also, on the other hand, we should go for always low cost technologies, obviously, to have a breakthrough for implementing the new non-conventional energy systems, which can replace the conventional energy use. Uh, what we are aiming here is the integration of the storage technology in the form of PCM, which work as a combined mode. Both sensible and latent heat are used in the energy system. So it belongs to the thermal application, very much suitable for this FDP you are undergoing during this week. We are concentrating on the solar water heater. We are incorporating the thermal energy storage in the form of phase change material PCM, and the flat plate collectors belongs to the two categories basically. One is the flat, I mean, solar water heaters belongs to two categories. One is the flat plate collectors, the old technology. Uh, the latest one in the field is evacuated tube collectors. In all aspects, these evacuated tube collectors are considered to be uh, superior to the flat plate collectors. Cost wise also, ETC collectors are somewhat cheaper compared to flat plate collectors. We are combining both modes of energy storage, both sensible heat as well as latent heat in the form of exchange materials. And we worked in encapsulation. That is one of the issues when we want to implement this phase change material. And we studied about the location where exactly we need to place this phase change material or the encapsulated PCM. And also we did some sort of stratification studies in the water tank. So that results also I'll be presenting towards the end. The operational efficiency we studied. Also parametric studies are made and comparisons are made with respect to experiment as well as uh, computational results, and also between various configurations there is a comparison made. uh, I'm going to present some results with respect to that. To start with, obviously any PhD student conduct sort of literature review in the field. I understand this particular student has reviewed more than
Sir,
100.
sorry, sir. Sorry, sir. Sorry,
Yes,
sir. Sorry
yeah,
to interrupt, sir. Sir, the slides are not changing, sir.
not changing.
Slides are
That
not
will
changing,
be
sir.
not changing. You should
Yes,
have
sir.
told. Oh, I'm already in fifth slide. Okay.
Yeah, okay, 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 sir.
Uh, okay.
Now it is okay, sir. It changed, sir. It's changed to fourth
N-
slide.
n-
Now it is in first slide. Second, sir.
Second, now it's fourth slide, right?
Yeah, fourth slide, sir. Okay, sir.
So when
Now it is in.
I change to slideshow, it is not changing.
Yeah, yes, sir. When you are changing to slideshow, it is not changing, sir.
What is the issue?
So no problem, sir. We can proceed with this, sir.
This is
Yeah,
okay.
yes, sir. This is okay, sir.
Okay.
We can proceed with this,
Okay.
sir. Thank
Okay.
you, sir. Thank you. Thank you.
So thank you for. Okay, I'll just quickly show the other slides. This is first slide I was talking, and second slide, uh, third one, and fourth. So any PhD student start with the literature review. As I understand, this particular student reviewed more than 100 related papers, and some of the papers are highlighted here. Uh, okay, I'll share this PPT after the presentation, so we may circulate with the participants. Okay. Uh, so uh, initially, as you all know, this solar water heater, which the work started in the 1970s in the basic book on solar thermal systems by Duffy and Beckman, you will see some mention about the solar water heaters. And this solar water heater system gradually started improving slowly from the basic water heater system to the present day solar water heater system in the form of ETC tubes. And if you think about the PCM integration experiments might have started in toward the end of last century itself. In the beginning of 2000 year itself, you will find some papers related to uh, PCM integration in the solar water heaters. So this is what 1998. There's a paper where we see a mention about PCMs which can be integrated in the solar water heaters. Okay, so at the bottom of this slide, I have given the name of that student. This is Dr. K. Dilip now, who graduated in the year 2020 with this particular work. Okay, so any PhD, we need to decide the basic objectives. In fact, these definition of these objectives are very, very important for the smooth going of the PhD work as well as the successful completion of the PhD work. So here he has stated. Normally, we state 4 or 5 objectives for the PhD work. And in fact, slowly you can update these objectives also as the work proceeds. And this particular work has five objectives. One is to conduct a preliminary outdoor experimental studies with two identical evacuated um, um, collector type solar water heaters and have a comparison. One of these collector is incorporated with macro encapsulated spherical balls having PCM. Other is ordinary standard ETC water heater. So initial comparison is made with respect to this. Then second objective is numerical modeling of a commercially available ETC collector. So this is made to have a sort of confidence in proceeding further when you are incorporating PCM in the ETC collector, how the numerical work can be done. The third objective is detailed numerical analysis to investigate the thermal stratification phenomena inside the tank, water heater tank. Then fourth objective is to design, construct, and conduct a real outdoor experimental work with ETC tube collectors integrated with macro encapsulated cylindrical containers. So this PCM now is incorporated in cylindrical containers. Then finally, to study now, if you want to incorporate cylindrical containers, how many containers you can incorporate, or how many will be more effective? That type of question arose. So that is the final objective, to study the effect of multiple PCM configuration and location of the macro encapsulated PCM containers and charging and discharging characteristics of PCM inside the water heater. So initially, these are the gaps identified by the researcher in this particular area. If you want to continue with the mm, PhD work, so some of these gaps he can address and try to find some conclusion with respect to these gaps. So first one is improving the thermal conductivity of the paraffin wax. So initially, most of the people use paraffin wax for their experiments. We also have used. Now the issue is paraffin wax is the conductivity. So paraffin wax has a low conductivity. Solar water heater, better conductivity. PCM will give better performance. So how to improve the conductivity of the paraffin wax? That is one of the gaps. Then the stratification phenomena. So the layers, different layers inside the water heater tank. We have water available at different temperatures. So different temperature layers are there in the water heater. So how these layers are separately remaining in the water heater tank. So that is an issue addressed. And third gap identified is how to increase the area of contact between the PCM containers and the surrounding water. So whether you are going to have uh, one ball, two ball, or multiple balls, or one cylinder, two cylinder, or multiple cylinders, and the area of contact, obviously, the more the area of contact, better will be the performance or heat transfer characteristics inside the water heater tank. Then how the number of PCM containers affects the performance, how the location of this PCM containers affects the performance, etc. And finally, we need to find out the optimum number of containers which can be kept inside the cylinder. So this is a very important question which need to be addressed, and hopefully this particular work give an answer for this question uh, given in the last line. The methodology followed is experimentation to compare the performance of identical water heaters with and without PCM, identification of the hindering factors for improving the thermal performance of the system, and experimentation to enhance the thermal conductivity, as I mentioned, by incorporating uh, float stones. Then numerical studies carried out with the help of ANSYS Fluent. Then validation of experimental results done and results are presented. And the determination of finally there is a functional relationship identified between the number of containers, I mean the cylindrical containers, and the corresponding duration of time required for completing uh, the melting process of the PCM inside the containers. Work layout will look like this. Initially, literature survey is carried out, and the selection of the ETC collector as well as the PCM for the experimental work is done. Modification of the existing system uh, carried out for the experiments to be conducted for this particular work. Then a comparison of experimental analysis with and without PCM, numerical investigation, and finally we concluded this. So to start with, the basic experiments done with the help of two collectors, you see here on the left side. One collector is an ordinary standard 200 liter solar water heater. The second collector on the right side is the collector in which the tank is filled with PCM balls. The PCM kept inside the uh, encapsulation by means of balls. So many such balls are put inside this tank you see here, and these two collectors are kept side by side so that simultaneously we pick out readings from these two collectors, and a comparison is made with respect to their performance. This gives the properties of the PCM on the left side bottom table. We have used paraffin wax as our PCM. On the upper side table gives the details of the solar water heater, which both are made of 200 liters. As I mentioned, one particular water heater have this encapsulated PCM balls inside the tank. So these readings are picked up by means of thermocouples. Temperatures are measured and flow rates are manually noted, and this temperature readings directly comes to the laptop through a data logger. So here you see the first result come out of this experiments. Uh, Left side you see the charging characteristics, and right side you see the discharging characteristics. Charging and discharging here, I mean the uh, uh, collection of heat, solar heat added to the water, and discharging. So we uh, drain water from the collector and see their performance. So charging characteristics you see between the collector PCM and with PCM and without PCM. The red lines corresponds to the characteristics of the collector with PCM, where you see a thermal inertia, note a thermal inertia here. So temperature gradually increases and finally matches with that of without PCM. Discharging characteristics on the other hand, so with PCM, the temperature reduction is more gradual compared to the collector without PCM. A rough energy calculation, lump type of energy calculation, you find initially itself, as I mentioned in the first slide, we could gain a percentage increase by about 10% in the form of heat storage capacity by incorporating the PCM in the solar water heater. So, the first phase conclusion from the preliminary experiments conducted here, nearly 10% of energy saving can be done, also shown by the calculations made. So, this can be made advantage in two ways. One is uh, the size of the conventional solar collector can be reduced by 10%. So, the existing solar collector, if you want to maintain the same capacity with respect to its performance, the size of the collector can be reduced by 10%. On the other hand, if you use the existing solar water heater with the same size and capacity, now by incorporating the PCM inside the solar water heater, we can enhance its capacity by 10%. So both are possible. This or that can be chosen depending upon the requirement. And this is with respect to 100 liter capacity system. If you go on multiplying the capacity, more and more capacity, you can imagine how much gain you can make, particularly if you want to implement solar water heaters in power plants for feed water heating purpose, etc. Large quantities of heat needs to be added in the water. So, by means of large capacity collector, so 10% increase will work out to a very large value in such cases. So, the phase 2 of this work is to study about the thermal conductivity enhancement of organic PCM by integrating float stones. So, this is one novel idea. We tried to experiment and produce some results. Conducted some basic experiments. This is the schematic diagram of the experiment model. One container here consists of paraffin wax, simple paraffin wax. Another container here you find paraffin wax added with float stones, and you will find the conductivity improvement. This is the float stone, basic float stone. The right side you see the float stones immersed in composite PCM, and these are macro encapsulated and experiments are conducted mainly to measure the conductivity, how much conductivity increase occurred when we incorporate these float stones in the PCM. So, this is the discharging characteristics of module with and without float stones. So, this again a set of experiments carried out with that basic water heater combination, and you will find obviously there is a additional advantage we gain by incorporating float stones in the paraffin wax. So, conclusion of phase 2, you will find this incorporation of this float stones, PMS PCM. We find there is a additional advantage in the form of this blue line shown here in the performance of the water heater. Now, coming to the actual core experiments of this particular work. Now, we have switched over to 100 liter capacity water heater, ETC type water heater again. So, initially we modified the tank with one cylindrical container. Then later we switched over to 3 cylindrical containers. You can see the cylindrical containers are added in the tank from one end to the other end. So 3 cylinders are added here, and experiments were carried out. Before that, we did basic experiments without this PCM added in the cylinder, and we made a comparison. And also the numerical work carried out is with basic water heater first, then adding this PCM cylinders, 1 cylinder, 3 cylinder and 5 cylinder. Numerical work results are carried out, and I'm going to present those results in the following slides. So experiments with and without phase change material. Now in this case, the phase change material is encapsulated in cylindrical containers inside the water tank. The entire working operation can be divided into two regions. One is the charging cycle, and other is the discharging cycle. Charging cycle is considered from 7 a.m. to 6:30 p.m., where heat is added to the water. And then after 6:30 p.m., the hot water is allowed to discharge from the solar water heater. And some experiments also performed with PCM integrated in solar water heater system, where PCM is used. The paraffin wax is used as the PCM, which has a melting point of 58 degrees centigrade and latent heat of 180 kilojoule per kg. Then experimental methodology, we have 4 different modes of experimentation carried out. First 3 modes refer to continuous discharge of hot water till the outlet temperature reaches 35 degrees centigrade, while the flow rate is different for each mode. So 3 different flow rates are done. Experiments are done with 3 different flow rates. So first 3 modes belongs to that. The fourth mode is the partial discharge mode, where the hot water is discharged in the evening at 3 liters per minute for 30 minutes, and the remaining hot water is discharged in the next morning until the outlet water reaches 35 degrees centigrade. So 35 degrees centigrade is kept as the base temperature for heating. So water drain is done until we reach 35 degrees centigrade in the outlet water. Now the cross section of the cylinder is shown here. We kept 3 different thermocouples. You see these layers are stratified layers inside the hot water tank. So bottom layer will have the lowest temperature, where we add at one end the cold water from outside, and the top layer is supposed to be the hottest layer inside the tank. And from the other side of the tank, we discharge hot water from the solar water heater tank. So all these are known to you. So we have 4 different modes of experiment chosen with PCM and without PCM. 3 different discharge capacities, continuous discharge capacities, 3 liters, 7 liters, and 15 liters. And the fourth experiment is the discontinuous or partial discharge mode, where we discharge 3 liters per minute for 30 minutes in the evening, and remaining hot water is discharged in the morning until we reach 35 degrees centigrade base temperature. Specification of the paraffin wax material, and the tank dimensions are given here. Solar water heater tank dimensions are shown here, and all details about paraffin wax also indicated here. This is the solar intensity variation in our location, NIT Calicut. 2 different months average is shown here. In the month of February and March, you find solar intensity in the March is little higher, and also we get some intermittent rains in the March month, pre-monsoon showers. So because of that, you find some distortion in the average solar intensity curve in the month of March. Now, the results indicate, as I mentioned, there were 4 modes of experiment carried out. When we discharge continuously 3 liters per minute, we see 2 lines here. The first line you see here is ordinary solar water heater, whereas the darker line indicates the PCM integrated solar water heater, where the temperature reduction history is modified accordingly. When we discharge 7 liters per minute continuously, there is a mild variation in the performance characteristics, as you see in this particular picture. Now, when we discharge at a higher mode, we notice fluctuation, obviously, because the large discharge rate create ripples in the tank, and the temperature fluctuation is noticed in the temperature, outlet water temperature. The mode 4, where we partially discharge in the evening some amount of water, then the next morning remaining water until we reach the base temperature of 35 degrees centigrade. So here you see in the evening discharge, in ordinary water heaters, you reach about 60 degrees, whereas PCM integrated, we reach about 55 degrees centigrade. Then remaining water, it discharge in the morning from that temperature. So there is a heat loss happening, and you can see the heat loss happen in the tank without PCM is much more compared to the heat loss that occur with PCM. So this can be an added advantage, particularly most of these domestic water heaters are utilized for hot water in the morning. So we during the daytime water heating happens, and in the early morning people start discharging water from the water heater. So during the operation also incorporating of this PCM substance inside the water heater found to be advantages during the operation of the domestic solar water heaters. So this is further result for mode 4, where partial discharge characteristics displayed in this picture. Now, conclusion of this phase 3 experiments carried out with and without PCM cylinders inside the water tank. Solar water heater with PCM cylinders and ordinary solar water heater. We notice low thermal conductivity of PCM affected the hot water extraction from the solar water heater, and the experimental analysis is successful, optimizing the PCM integrated in the solar water heater so that maximum amount of hot water extraction is possible. The proposed system is capable of providing about 90 liters of hot water in the evening above 60 degrees centigrade, and about 45 liters of water in the next morning above 45 degrees centigrade, which is operated at the suggested flow rate, when it is operated at the suggested flow rate. So here you find, even though the water tank capacity is 100 liters, we experimented, we get about 135 liters of hot water, even 100 liters, around 100 liters at 60 degrees, remaining 30-40 liters of water heater at 45 degrees, above 45 degrees centigrade is possible to get from this water heater if we incorporated the phase change material inside the cylinders. Now coming to the second segment of this particular PhD work, mostly done by ANSYS Fluent this numerical investigation. Again, many phases are available for this particular numerical work. I will quickly present the most important features of this numerical work carried out with respect to ETC collector with and without PCM cylinders incorporated. So first phase is numerical analysis of ordinary ETC solar water heater for assessing its basic performance characteristics. Our aim here is to gain confidence in the numerical analysis to prepare a numerical model for the ordinary domestic solar water heater, analyze its charging and discharging processes separately, study the effect of discharge flow rate on the evaluation of the thermal layers, stratified layers inside the hot water tank of the solar water heater, and to develop a numerical model and validate it against the experiments conducted earlier with the help of ETC collectors. And the system is allowed to get charged continuously throughout the day by means of solar energy. So this is the geometrical model created for the numerical analysis. A 100-liter capacity ETC type solar water heater. You see the hot water tank and the tubes modeled in the ANSYS bench, and the parameters and the corresponding dimensions are given here for the numerical model. The basic assumptions made, the flow is considered to be Newtonian, laminar, three-dimensional and incompressible. Ordinary assumptions made. Thermophysical properties are assumed to be constants. Obviously, natural convection is happening. Thermosiphon effect is considered in the form of Boston's approximation. The viscous dissipation is considered to be negligible, and there is no inflow or outflow from the collector while we are charging the collector with solar energy. Initial temperature of the whole system is assumed to be constant at ambient temperature. So the governing equations are standard governing equations, the form of continuity, momentum, and energy equations. And beta value expression is given here. And the storage tank is having 5 centimeter thick puff insulation all around. In order to account the heat loss through the insulation, the overall heat transfer coefficient is calculated with the help of the expression given here from one of the references. And solar intensity profile is created using a fourth order polynomial from the average curve I shown earlier for the month of March and February. A fourth order polynomial with the help of a curve fitting tool in MATLAB, we get this expression, and the 5 constants involved in the fourth order curve is also found out and listed here. The direct radiation is given in the top part of the ETC, whereas the reflected radiation is given at the bottom part. So some amount of reduction is given for the reflected radiation from the bottom side of the tube. The calculated heat loss coefficient is given in the storage tank walls in order to account for heat loss through the system. So this is the profile I showed earlier. Now with the help of curve fitting, a fourth order polynomial indicated in the last slide, we will get this smooth graph. So this particular input is given for the solar insolation for the collector. At the top side, full intensity; at the bottom side, some amount of reduction, maybe 50 or 60%. So top layer temperature is indicated here. The aim of this particular graph is to identify the number of grids we need to use for the further calculations. So this we call it as grid independency test, which is very essential for any sorts of numerical work we do. So here more than 1 lakh grids were utilized, and finally he arrived at something like 1.62 lakhs of grid is good enough for conducting further numerical studies, both with and without PCM in the solar collector. So this is the picture of the mesh used for the analysis, and the number of mesh elements shown here is more than 1.3 lakhs. Then orthogonal quality is given here, skewness is given here. These two are important parameters. So this should be around 0.9 or more. We get about 0.89 here, and skewness should be 0.2 or less. We get about 0.22. So the validation of the model is carried out. The numerical results obtained is validated against the experimental results conducted at a particular day. Then charging, the system is allowed to heat up throughout the day until 6:30 p.m. without any drain from the collector. Average temperature within the storage tank at 7 a.m. is taken as the initial temperature of the numerical analysis, that is very close to the ambient water temperature. Then discharging, the discharging process started at 6:30 p.m. and continuously at a constant flow rate of 3 liters per minute, and the experiment conducted until the outlet temperature reaches the base temperature value of 35 degrees centigrade. The temperature profiles inside the tank during charging and outlet temperature profile during discharging is validated against the conducted experimental results. So this is the picture for the validation of the experimental results, and you get 3 different temperatures from 3 different thermocouples fitted in the tank. As I showed earlier, these 3 thermocouples are fitted at 3 different locations, one at the bottom of the tank, other at the center of the tank, other at the top of the tank. Top temperature, you see the variation. There is a marginal difference comes as we proceed with the time, the difference between experimental and numerical results. At the center also we notice some sort of difference here, whereas the bottom side temperatures matches very close with the experimental results. And in all these graphs you find the trend is matching exactly. So with this sort of confidence we proceed further. This is another validation for the model. Experimental versus excuse me. Somebody is asking something. Okay, there is some disturbance. Okay, so this is another validation, model validation between experimental and numerical results. Temperature profiles inside the tank during charging, and we are seeing here the 3 different thermocouples temperature values from the numerical result. This picture shows the velocity vectors. You can see very clearly the velocity vectors indicating there is a water flow happening at the bottom side of the ETC tubes. From the tank, water enter inside the ETC tubes. At the top side of the ETC tubes, you find the water returns back. So the thermosiphon effect is very clearly depicted by these velocity vectors in this particular picture. Here you are seeing the temperature contours produced by the numerical analysis, and after the full charging occurred with respect to the solar energy addition, you find the hot water exists at the top side of the water tank, and bottom side you see the temperatures are lower. Here you see around 332 Kelvin, whereas bottom you see about 341 Kelvin. Around 10-degree difference in temperature occur inside the hot water tank. So stratification very clearly indicated in this contour plot. So the discharge time is made non-dimensional using the following equation. Time is non-dimensional with the help of the time required for achieving 35 degrees centigrade discharge temperature. So with dimensionless time on the x-axis, the temperature graphs are shown here for 5 different discharge rates used in the experiments. Now, as I mentioned, stratification of thermal layers is a very important characteristics. So this is identified with the help of, or studied with the help of a number, non-dimensional number called stratification number. You'll find this definition and details in this particular reference, Fernandez and Sierra, where stratification number is defined like this, and the right hand side parameters are indicated here in equation 8 and 9. So the stratification number on the y-axis, dimensional time on the x-axis, we see the various graphs with low discharge rate. We find the stratification number is larger, which is the preferred characteristics with respect to solar water heater inside the hot water tank. Another temperature contour for the storage tank, when we discharge water at different rates, 5 liter per minute, 10 liter per minute, and 15 liters per minute. So at some particular after some particular amount of discharge happened, this picture shows after 90 liters of discharge occurred in these 3 different cases, how the temperature contour inside the tank will look like. So as obviously with large discharge rate, you find the stratification becomes lesser and lesser. So conclusion from phase 1 of the numerical work carried out. As I mentioned, this particular phase 1 numerical work is to gain confidence done with ordinary solar water heater, ETC type water heater, without any modification incorporated inside the tank. So we understood thermal stratification plays a significant role in extracting hot water at higher temperature from the tank, and the developed numerical model was able to simulate charging and discharging processes. There is a stagnant region at the bottom of the storage tank created due to inclined position of the ETC, and the discharge flow rate is increasing hot and cold water mixing inside the storage tank is increasing. Higher mixing causes an early drop in the outlet water temperature during discharging. And until 7 liters per minute flow rate, the outlet temperature with respect to time tends to seem almost similar. So these are the basic conclusions made. And with this initial confidence and experience with the numerical work, uh, he proceeded further with the numerical analysis uh, to assess the role of operating variable on the outlet temperature. Okay, so here the ETC type direct solar water heater modeled. Again, the geometry is shown here. Uh, uh, ANSYS Fluent package is used for the analysis. So this time the numerical experiments are carried out with 200 liters water heater. The mesh generated, and this model consists of about 1.8 lakh tetrahedral elements. On the right hand side, you see the tetrahedral elements shown here. The boundary conditions indicated here. Density variation is considered with Bosnian approximation, and the thermophysical properties used for the analysis are listed here in this table. The results indicate here the grid independence test carried out for this 200 liter capacity water heater, and finally we decided on the number of grids to be used for the further analysis. The heat flux of different values are considered for the numerical experimentation. Flow rates are varied from 0.02 to 0.04 kg per second for this 200 liter water heater, and 6 different heat fluxes. Again, every time we considered constant heat flux, as you know, the heat flux is continuously varying, solar heat flux, but for this numerical experimentation, average heat flux at constant rate is considered for the analysis. Again, I don't want to spend time on this. This is repetitive graphs where the temperatures are shown with respect to different flow rates and different heat transfer, heat influx values, solar heat influx values. And temperature contours are shown here for this particular analysis. And conclusion of this phase 2. So buoyant forces and gravity have greater role to play in the circulation of water within the ETC type solar water heater. Higher solar intensity and lower mass flow rates proved to have significant improvement in the outlet water temperature obtained from the collector. Now, this phase, I mean, the third phase of this numerical analysis is important, where we integrate the PCM cylinders in a solar water heater. Now we start with a single cylinder cylindrical container, then increase it to 3 cylindrical containers, and then finally 5 cylindrical containers. All these cylindrical containers, all these 3 categories, we keep the amount of PCM constant. Only thing, the total PCM is either kept in a single cylinder inside the water tank or in multiple cylinders, so that we could arrive at how many cylinders is better and what location of these cylinders are better. So that is the aim of this particular phase of this particular work, and this is considered to be the most important phase of this PhD work. So, with single cylindrical containers, the liquid fraction is indicated here. So, as time proceeds in hours, with for about 3 hours plus, we find there is no melting happens. The melting starts after 3 hours, and slowly the liquid fraction goes on increasing. And our final aim, obviously, is to get liquid fraction 100%. So with single cylinder, we could not get that 100% liquid fraction even after 7 or 8 hours of heating. So with respect to the time, you find the temperature variation also indicated on the right hand side picture. If you see the cross section of the water tank, the PCM is kept in a single cylinder. So in the total tank cross section, at the center, you find the PCM cylinder. So after 3 hours, even after 3 hours, you find the PCM is remaining as it is without any melting. So melting starts after 3 hours, as you see from the previous graph here. So after 3 hours, the melting starts. So 3 hours picture shows this, no melting. So when you see the same picture after 5 hours, you find the melting started. Some amount of PCM got melted at the outer boundary of the PCM cylinder. And this phenomena goes on increasing, and the melt content goes on increasing. By about 7 or 8 hours, you find something like 60 to 70% of PCM got melted. This contour picture shows the temperature inside the tank. So the cross section indicates the temperature contours. So as the PCM remain its base temperature in 1 hour, then 3 hours, at 5 hours, and only after 7 hours you find some amount of melting happened in the PCM, and also the temperature surrounding got increased. Now the discharging characteristics with 1 liter per minute, 2 liter per minute, and 3 liter per minute. So 1 liter per minute, gradual temperature change with respect to time. Further, faster temperature change with 2 liter per minute, and with 3 liter per minute, the temperature change is sharp. Whereas the liquid fraction during discharge, similar characteristics indicated in the second picture. The evolution of thermal layers during discharge is indicated in these pictures. As we discharge hot water from the water tank of the solar water heater, cold water enters here, and the temperature gets compensated and goes back to its lower temperature. So the PCM also slowly gets solidified. So from here, remember, after 7 hours of heating, we start discharging. After 1 hour of discharging, we find some PCM got solidified. Then after 2 hours, you get further PCM solidification, and after complete discharge, maybe 3 or 4 hours, you will find the most of the PCM got solidified. So here at the bottom side, you see the evaluation of thermal layers during discharge, 60 minutes, 90 minutes, and 120 minutes. Conclusion from phase 3, as I mentioned, with 1 cylinder incorporated, PCM incorporated in the incorporated in the water tank. Uh, the analysis revealed that flow rate discharge has an effect on the outlet temperature characteristics of the hot water, and clearly the effect is indicated in the graphs. And poor thermal conductivity causes delay in the solidification of PCM, as you see in the previous slide. Then configuration chosen for the analysis cannot fully melt the PCM within the period of charging possible during the day of sunlight available. This conclusion is very important. The last conclusion is very important. We have used one cylinder of one cylinder PCM fitted inside the water heater. So the lower thermal conductivity of the PCM hinders the complete melting of the PCM, and also for its operation in a domestic solar water heater during the daytime when heating occurs, we could not completely melt the PCM inside the cylinder. So the question comes, how we are going to sort out this issue. So we proceed with further numerical experimentation with increasing the number of cylinders inside the water tank. So first with 3 cylinders, then further we enhanced with 5 cylinders and carried out the numerical experimentation in the same solar water heater having 100-liter capacity. And remember, the total quantity of total volume of the paraffin wax we fitted inside the cylinder remains same. The design considerations here. We are assuming that the water heater temperature should increase from 30 degrees to 65 degrees centigrade. That is the domestic water heater requirement. So energy storage, amount of energy stored can be calculated with the basic formula here. Mass of water contained in the tank is 100 kg, and by calculation the stored energy stored by water is 14,651 kilojoule. Now the PCM is integrated in the water heater system, and it is designed to store 110% of total energy obtained, because our aim is to enhance 10% increase in the total energy storage. So we find that the volume of PCM required is about 22 liters. So how we are going to incorporate this much quantity of PCM inside the water heater tank? So initially with one cylinder incorporated inside the water heater tank, one PCM cylinder I mean. Then second case is with 3 cylinders inside the tank, and third case is with 5 cylinders. Material used is paraffin wax as before, with the properties mentioned here in the table, and pressure velocity coupling for the numerical analysis is piezo. So again, the usual assumptions are made. The fluid is considered to be Newtonian, flow is laminar and incompressible, and water tank is considered to be perfectly insulated. No heat loss or gain occur in the water tank. Thermophysical properties are assumed to be constants, and volume expansion is PCM is ignored during its phase change. And Bose-Nash approximation, obviously, because we are using the thermosiphon effect. No inflow or outflow happens while charging with solar energy. Initial temperature of the whole system is assumed to be constant, and the time taken so governing equation, continuity equation, momentum equation, and energy equation at the bottom. And liquid fraction is calculated using this formula number 15 indicated here, and enthalpy change is calculated with the equation 16. Boundary condition, the top part of his ETC is considered to be having a heat flux constant at 800 watts per meter squared. Bottom part, as I mentioned, with the reduced heat flux in the form of reflected solar radiation. So we consider about less than 50% of the heat at 300 watts per meter squared. No heat gain occurs or heat loss occurs through the walls of the water tank. No heat gain or heat loss occurs through the evacuated water tube. So insulated boundary is considered for the numerical analysis. So initially grid independence test as usual. Here results are presented in the form of tables. So for this numerical experimentation has gone to the extent of something like 3 lakh elements, and finally arrived at its required number of elements for the analysis. So mesh details for the 3 different numerical experimentation he has carried out with 1 cylinder, 3 cylinder, and 5 cylinder. Very clearly the mesh is depicted here in these pictures. The cross section of the water tank is shown here very clearly with 1 PCM cylinder here on the left side. In the middle you have 3 PCM cylinder, and the right side you have 5 PCM cylinders. Coming to the results, the contours of liquid fraction after 3 hours for the 3 different cases indicated here. After 3 hours you find water is getting heated, red color, whereas the PCM remain without melting. Maybe minor melting occurred at the boundaries only, which is not clearly seen in these pictures indicated. Whereas after 5 hours, we clearly see the variation. This is a very interesting contour picture. You see about the liquid fraction for single cylinder. The melting is occurring only at the boundary. Obviously, the melting occurs only at the boundaries of the cylinders. But for single cylinder, the melting fraction is less compared to the multiple cylinders. 3 cylinders is more, and with 5 cylinders, you get large amount of melting occurred by the time you reach 5 hours of charging with solar energy. Whereas after 7 hours, you see with 5 cylinders, you get totally the PCM melted 100%. Still, you find some minor solid spots in the PCM cylinders. Whereas the single cylinder, it's still remain dump without melting in the middle portion. More than 50% of the PCM remain without melting in the cylinders. So this graph indicates time versus the liquid fraction, and with 5 cylinders, somewhere around 5 to 6 hours, you get 100% melting occurred by that time. Whereas with 3 cylinders, this 100% melting require even after 7 hours for the 100% PCM to get melted. Now, if you look at the temperature plots, contour plots, after 3 hours, it will look like this. In the single cylinder case, you get very low temperatures occurring at the middle portion of the PCM cylinder, whereas in 3-cylinder, the temperature got increased, whereas 5-cylinder, more or less, we get uniform temperature everywhere. After 5 hours, then after 7 hours, you get in the 5-cylinder case, very uniform temperature distribution in the contour plot. So in a XY plot, you can see the same pictures, characteristics indicated with respect to time, the temperature variation for both 1-cylinder, 3-cylinder and 5-cylinder cases. This can be considered as a major contribution or finding generated by this particular PhD work. The variation of temperature during the melting with respect to time and the number of encapsulation cylinders kept inside the tank. Because as I mentioned in the beginning, our aim is to go for how many cylinders of PCM that can be kept effectively for the best performance of the domestic water heater. And we could arrive at a reasonable conclusion that with 5-cylinder itself, we could get our aim satisfied, whereas 3-cylinder gave reasonably good performance, and this is fitted in a curve with the exponential function here, and this curve fitting is done and published. Here you see the vector plot very clearly indicated with the help of one particular cross section at the middle of the ETC collector. So the ETC tube and the water tank, how the movement happens inside the cylinder after fitting the encapsulated PCM cylinders inside the tank. So the hot water gets heated in the PCM container and flows around the water tank. Whereas in a 3-cylinder tank, the movement is like this, and in the 5-cylinder, particularly if the ETC tubes are fitted in a position something like this, then you get a more or less uniform circulation happens by natural convection inside the hot water tank. Conclusion from phase 4, the most important phase of this particular work. We generated a numerical model which is able to visualize and predict the behavior of the latent heat storage unit integrated inside a ETC solar water heater. Then the objective of the numerical analysis is to determine the favorable encapsulation of the geometrical configuration, whether it's a ball type or cylindrical type, which can be integrated inside the solar water heater. So we found that the cylindrical type is better. The analysis was conducted using single cylinder, 3-cylinder and 5-cylinder in the numerical analysis, and obtained results suggest that 5-cylinder configuration is the best, whereas 3-cylinder configuration also could provide satisfactory result. The reduction in melting time is evident as the number of cylinder increases, but the rate of reduction is observed to be reduced as the number of cylinder increased, obviously. Okay, so with this, I stop my presentation. Some of the references are indicated here. As I mentioned, I will circulate this PDF with the organizers so you can get. And thank you for your patient hearing. And I pass it on to the organizers.
Yeah, sir. So thank you so much, sir. So I like to
Yeah.
take this opportunity to thank Dr. S. Jayaraj, sir, Professor NET Calicut, for sparing his valuable time with us. Thank you so much, sir. The session was a perfect blend of experimental and validation with CFD, sir. These type of sessions involving both are much needed of the hour when it comes to publication. As many of us know that producing only experiment results are less interested among researchers unless a path-breaking results are produced. So thank you so much, sir, for giving us a wonderful session. Thank you so much,
Thank
sir.
you. Thank you. Okay. I'm just seeing if any questions are there. Otherwise, you can conclude.
Participants, do you have any questions? You can raise to the resource person.
Sir, so can I ask you a question?
Yeah, sir. Please.
Yeah, sure. I'm hearing you.
Sir, is there any difference in the hard water and normal water, especially in terms of temperature gain, temperature existence, or the heat gain or heat loss?
You mean hard water, hard, HARD.
Yeah, because some substances sometimes after a period of time
Yeah.
it will be
Yeah.
deposited on the
So,
walls. No?
yeah, hard water, you can expect some minor variation in the performance, but the major problem with hard water is with respect to the life of the collectors. Okay, so not in the performance, routine performance of the collector. So it drastically affects the life of the solar water heater. So it is preferred that we do some sort of treatment before, if the water is very hard, then we do some sort of treatment before we pass it on to the water heaters. Okay.
Okay, thank you.
Participants, do any other have any doubts? Okay. So your feedback link has been posted in the chat box. Kindly do fill the feedback.
Okay, organizer, I will just now mail you the PDF of this PPT.
Sure, sir.
So you can circulate in whatever way you feel like
Sure, sir.
that PDF. And if anybody is seriously interested in the PDF of the PhD thesis I mentioned, that also I can share with them personally if they mail to me. Okay?
Sure, sir. Sure, sir. Sure, sir.
Okay.
Thank you so much, sir. Thank you so much for your time, sir.
Thank you. Thank you for the participants for your patient hearing. I understand more than 75 people are watching, and I'm wholeheartedly thank you for your patient hearing, and have a nice day. And I wish all success for the organizers of this FDP.
Thank
till
you,
the
sir.
end.
Thank you so much, sir. Thank you so much, sir.
Thank you. Have a nice day. Bye.
Yeah, sir. Thank you, sir. Participants, kindly fill the feedback link which was posted in the chat box. Yesterday, feedback link also has been posted. So those who are missed that to fill the feedback, you can fill that feedback also. We have posted both the sessions feedback, yesterday's and today's feedback. Kindly do fill the feedback. So participants, those who fill the feedback, you can leave the session and you can join by afternoon 2 p.m. And the session will be handled by Dr. Anthony Michael Ratza. So you'll be handling on CFT. So you can join the session by 2 p.m. Those who fill the feedback. Thank you so much for your time.